Welcome back, everyone. Ready for another deep dive?
Always.
Well, today we're tackling a paper that really shook things up in AI, specifically in natural language processing, or NLP.
Ah, yeah. Attention is all you need.
That's the one. This paper, it wasn't just about a new model, it was a whole new way of thinking about some of the toughest challenges in the field.
I'd say even beyond NLP. We're seeing the ideas from attention is all you need popping up everywhere, from computer vision to even music generation.
It's amazing to see how one paper can spark so much innovation. But for those who might not be familiar with the NLP landscape before this paper, can you remind us what the big problem was that this paper was trying to solve?
Sure. So imagine you're trying to understand a story, right?
Okay.
But you can only read one word at a time. You might get the gist, but you'd miss all those connections, the subtle references that make a story truly captivating.
You mean like those long-range dependencies we hear so much about in NLP?
Precisely. And that's where those older models, those RNNs or recurrent neural networks, really struggled.
So they were like reading with blinders on?
Perfect analogy. They were fine for short bits of text, but give them a long paragraph or a whole document. Forget about it. Plus, they were slow, really slow to train.
So how did attention is all you need change the game? I know it introduces this thing called the transformer, but what makes it so revolutionary?
Well, think of it this way. The transformer, it throws out the rule book. It doesn't go word by word like those RNNs. It looks at the whole input, the whole sentence, all at once, figuring out which parts matter most to each other. Like a team of experts, each focusing on a different piece of the puzzle, and then they all come together to give you the full picture.
Ah, so that's where attention comes in. Right.
I-
But this isn't like my dog perking up when he hears the treat jar, is it?
Haha, well, maybe there are some similarities. In AI, attention lets the model focus on the most important parts of the input. Just like when you're reading, you focus on certain words or phrases to understand the meaning. The transformer, it figures out which parts of the input are most connected.
So it can see those long-range dependencies that the RNNs missed.
Exactly. But there's another challenge. If it's looking at everything at once, how does it know the order of the words? That's got to be important, right?
Yeah, word order is everything in language.
Absolutely. And the transformer has a clever way to handle that. Positional encodings.
Positional in
Basically, they're like timestamps for each word, telling the transformer where it falls in the sequence. So even though it's processing everything in parallel, it doesn't lose track of the flow of information.
That's brilliant. It's like the transformer has this internal clock keeping everything in sync. But I still don't quite get how it figures out which words are most important to each other. What's the secret sauce there?
The secret sauce? Well, it's a bit technical, but imagine you've got a question. In the transformer world, we call that a query. And you're searching through a library of documents, right? Each document has a title, a key, that gives you a hint of what's inside. You compare your question, your query, to each title, and the closer the match, the more likely you are to open that document to find your answer. The document itself, that's what we call the value in this analogy.
So in the transformer, the words are acting like both the questions and the documents. Each word is trying to figure out which other words are most relevant to it.
Exactly. And the dot product part you might hear about, that's just a fancy way of measuring how similar the query and the key are. The higher the dot product, the more connected the words.
Okay, it's starting to make sense.
Hmm.
But you said scaled dot product attention. What's the deal with the scaled part?
Ah, that's all about those long-range dependencies we talked about. Without getting too deep in the weeds, the scaling helps the transformer handle those longer connections without getting confused. It's like making sure the signal doesn't get too strong and drown everything else out.
So it's a safety valve, keeping those long-range connections in check.
You got it. But wait, there's more.
Oh boy.
We've also got this concept of multi-head attention. It's not just one attention mechanism at work, it's multiple, each focusing on different aspects of the input.
So like having multiple detectives all examining the same evidence but looking for different clues.
Precisely. This gives the transformer a much deeper, richer understanding of how words relate to each other in a sentence. It's not just the obvious connections, it's those subtle, underlying relationships that make language so complex and fascinating.
Wow. This attention mechanism is way more sophisticated than anything those RNNs could handle. And to think, we've only just scratched the surface.
We've got a lot more to unpack.
Well, then let's dive deeper.
All right, so ready to see what's happening under the hood of this transformer?
Absolutely. I'm all about the nuts and bolts. We talked about attention, positional encodings, all that good stuff. But how does it actually learn from data? How does it, go from a bunch of words to a coherent translation or a parsed sentence?
Well, you can think of the transformer like a network, right? A complex network with all these interconnected layers, and each layer has its own specific job to do.
Layers. So it's not just one big blob of attention.
Oh, no, no, no. It's much more structured than that. We've got, for example, the encoder and the decoder. These are like the two main branches of the transformer.
Encoder-decoder. Okay, I'm listening.
So the encoder, that's the part that takes the input, let's say a sentence in English, and transforms it into this rich representation that captures all the meaning, the relationships between words. And then that encoded information gets passed over to the decoder, which uses it to generate the output, maybe a translation into Spanish or, whatever task we're doing.
So the encoder is like the interpreter breaking down the input, and the decoder is the writer putting it all back together in a new language or a new form.
That's a great way to put it. And within both the encoder and decoder, we have those attention mechanisms we talked about. That's what lets the model focus on the most relevant parts of the input at each stage.
Ah, right, those scale dot product attention things with the queries, keys, and values. I'm still trying to wrap my head around how it does all that in parallel, figuring out which connections matter most.
Well, it's a symphony of computations happening all at once, but attention isn't the only thing going on. There are also these things called feed-forward networks in both the encoder and the decoder.
Feed-forward networks. What do those do? Are those different from the attention thing?
Yeah, they're different, but they work together. Attention is all about relationships between words, right? Feed-forward networks, they focus on each word individually, kind of refining its representation based on what the attention mechanisms have discovered.
So it's like each word gets its own little makeover based on the information gathered from its interactions with other words.
Yeah, you could say that. They fine-tune the details, making sure each word is represented in a way that captures its specific meaning within the context of the whole sentence.
It's really thorough. It's like the Transformers leaving no stone unturned, considering both the big picture and all the little details.
And here's the kicker. All of this happens multiple times within the encoder and decoder. The transformer uses what we call stacked layers, meaning these processes, the encoding and decoding, they're repeated several times with the output of one layer feeding into the next.
Stacked layers. It's like building a skyscraper. Each floor adds another level of complexity to the whole structure. But why repeat the process? What's the advantage of having all these stacked layers?
Each layer, it kind of digs deeper into the meaning, builds upon the representations created by the previous layer. In the encoder, you're understanding the input more and more deeply with each layer. And in the decoder, you're refining the output, step by step, making it more accurate and fluent.
So it's not just about processing the information once, it's about refining it, enriching it through multiple stages, like polishing a rough stone until it becomes a sparkling gem.
I like that. That's a great way to visualize it. And this multi-layered approach, that's a big part of why the transformer is so powerful. It allows it to capture these really complex patterns and relationships in the data.
Okay, it's amazing to think about all these processes happening at once. But how does the transformer actually learn? We've talked about the architecture, but where does the learning come in?
Well, like any machine learning model, the transformer needs to be trained, right?
Right.
Trained on a huge amount of data. Think millions, billions of examples. In the case of translation, that would be tons of sentence pairs in different languages.
So it's learning by example, like seeing how human translators...
All these example sentences, it tries to predict the correct translation, and then its predictions are compared to the actual translations, the ground truth. And based on the errors it makes, it adjusts its internal parameters.
So it's like a process of trial and error, constantly tweaking its approach until it gets better and better.
Exactly. And this happens over and over and over again, millions of times. The model keeps refining itself, becoming more accurate, more fluent, until it can produce translations that are as good as, sometimes even better than, human translations.
That's remarkable. It's like the Transformers going through its own language immersion program.
You could say that. And what's really impressive is that this whole training process, it's remarkably efficient thanks to the Transformer's parallel processing. Remember how we talked about those RNNs that had to go word by word?
Yes, super slow.
Well, the Transformer, it can process whole sequences at once, so training is much, much faster.
That's what's so exciting about this paper. It's not just a new model. It's a solution to some of the fundamental problems in AI. Faster training, better performance, the ability to deal with those long-range dependencies that used to trip up the RNNs. It's like a trifecta of innovation.
You're absolutely right. This paper, it really opened up the floodgates for larger, more complex language models.
It's like unlocking a whole new level of potential, not just for NLP, but for AI in general.
Yeah.
It's amazing what can happen when you start thinking outside the box, challenging those old assumptions.
And speaking of thinking outside the box, one of the most exciting things is how the transformer's influence is extending beyond NLP. Researchers are applying these ideas to all sorts of things, from image recognition to music generation. The results are mind-blowing.
That's what I love about this field. It's constantly pushing boundaries. Okay, I think we've covered a lot of ground here, going from the basic architecture to how the transformer learns to its broader impact.
Yeah.
But before we wrap up, I want to circle back to those remarkable results we talked about earlier, the ones that really put the transformer on the map
Yeah.
of those mind-blowing results. Remind us what made everyone pay attention, so to speak.
Well, they tested the transformer on this standard benchmark in machine translation,
Okay.
the WMT 2014 English to German task. And the results were, well, they were groundbreaking. It set a new state-of-the-art BLEU score.
BLEU score, that's how we measure how good a machine translation
Yeah.
is, right?
And it wasn't just a small improvement. The transformer, it just blew past all the previous models.
Wow, so it wasn't just a little bit better, it was significantly better.
Oh, yeah. And not only that, it did it in way less time. Like, RNNs might take days or even weeks to train on a data set like that. The transformer, it did it in hours.
That's a huge difference.
Yeah.
I mean, not just saving time, but it opens up so many more possibilities. Researchers can try out new ideas, experiment with bigger data sets, things that just weren't feasible before.
Exactly. The transformer, it wasn't just a faster model. It was a whole new way of thinking about these problems, a real paradigm shift.
And we talk about how it was good at other things too, not just translation. Like that English constituency parsing task.
Mm-hmm.
What was that about again?
Right. So parsing, it's basically analyzing the grammar of a sentence, breaking it down into its parts.
Kind of like those sentence diagrams we did back in school.
Exactly. But way more complex, obviously. And this is something that traditional NLP models, especially those RNNs, really struggled with because of those long-range dependencies, remember?
So for the transformer to be so good at this, it really shows how well it understands those connections between words, even when they're far apart. Like it's got a real grasp of grammar.
Exactly. And the fact that it could do so well, even with less training data, well, that tells you something about how well it can generalize, how adaptable it is.
This is all very impressive.
Mm.
But there's got to be some downsides, right? It can't be all sunshine and roses.
Well, no model is perfect. The transformer, it's incredibly efficient for long sequences, but when you have shorter sequences, it can be a bit computationally expensive. All those calculations, those dot products, they add up when you've got lots of words to compare.
So it's not a magic bullet. There are still trade-offs depending on what you're trying to do.
Right. But that hasn't stopped researchers from improving on the original transformer. There are already variations out there that are even better, even more versatile. It's a very active area of research.
It's amazing to think how much progress has been made just since this paper came out. And it really makes you wonder what's next. What other fields could the transformer revolutionize? What other problems could it help us solve that we thought were impossible?
Who knows? We're already seeing its impact in image recognition with models like the Vision Transformer. People are applying it to music generation, drug discovery, even predicting protein structures. The possibilities are truly endless.
It's like this one paper opened a door to a whole new world of possibilities. And to everyone listening out there, I challenge you to think about how this idea of attention, how it might be applied in your own work, your own life. It's a powerful way to understand complexity, to see those connections that we might otherwise miss.
It's all about asking the right questions, challenging the status quo, and looking for new ways to understand the world around us.
Well said. Thanks for joining us on this deep dive into Attention is All You Need. It's a paper that has truly transformed the field of AI, and its impact will continue to be felt for many years to come.
Absolutely. And until next time, keep exploring, keep learning, and keep paying attention.